Okay, so you have so far named compounds that are made of just simple monatomic ions. You've done stock nomenclature for things that have variable cations because they're made of metals. And now we're going to talk a little bit about polyatomic ions and compound naming with polyatomic ions. You already know what a polyatomic ion is. You've drawn them. You've drawn everybody's favorite. Okay, and by that I mean nobody's favorite. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And all the resonance structures therefore, that's called a nitrate ion. That's what you've been drawing. For time's sake, I'm going to save myself that. You've drawn sulfate ions. You've drawn these things. And so what you know is that these are atoms that are bonded together covalently. They're sharing electrons, but then the whole group has either picked up an extra electron or given up an electron. These are mostly the ones that we're going to deal with are mostly what are called Oxy Anions. They're the most common. We have a few that we deal with that are not. Oxy meaning it contains oxygen. Oxygen! They're not really creative chemists. Not creative at all, actually. So Oxy Anions are what kind of ion? Negative ions, anions, that contain oxygen. Woohoo! And if you look at the list that I gave you, you will see that the vast bulk of ions you've got there are negative. There are only really 2 cations that are polyatomics that we deal with ever. And every single one of those anions has oxygen in it, often multiple oxygens. So here's the tricky part. Do you remember when I said early on, like, pay attention to IDE? It seems like it's just an ending. You need to be really conscious of the fact that it's important. Now we're at the point where it super matters. Because when we get into the polyatomic ions, we start to see ATE and ITE. And I remember as a high school student and later as a college student trying to memorize the pattern. So it's not memorizable. It's only practicable. And once you've practiced it, you will not mix up nitrate and nitrite. The most common ion is given an ATE. Whatever occurs most in nature gets ATE. So if you would be so kind as to look at your ion reference and look at NO3 1 minus and NO2 1 minus on your ion reference. Tell me which one is more common. NO3 1 minus, yeah, which is the nitrate ion. Because it gets the ATE ending, it's the most common. If you have one less oxygen than whatever is most common, you get an ITE. So we have nitrite, which is one less oxygen than the most common. Great. So 3 oxygens is 8. No. No, not that easy. If you look at SO4 2 minus and SO3 2 minus, which one is most common of these two? SO4 2 minus is sulfate. So that's your most common. SO3 2 minus is sulfite, and so it gets the ITE ending. Pay attention to ITE, ATE, IDE. Ide, ate, and ite. Now there are a couple others. We don't see them much. Chlorine forms a whole bunch of polyatomic ions, and these are listed on your sheet. So we'll start with the most common, and my spacing got shifted. ClO3 minus is chlorate. That's the most common chlorine-containing polyatomic oxy anion. Chlorite, ClO2 1 minus, has got one less oxygen than the most common. Well, and it's rare. We don't have, that I know of, this doesn't occur with other ones, but you can have 2 fewer oxygen than the most common, and then you get a hypoite. Really? Yes, really. You can have one more than the most common and you get a per 8. Here's the deal. Be aware of those sounds. Know what they are. You're never going to do anything without this again. You're going to have this on homework. You're going to have this on tests. You're going to have it on labs. Anytime that you're doing anything, you're going to have this chart with you. Here's the dirty secret. So when I was in high school, we had to memorize polyatomic anions. And it was the same kind of deal, actually. You could take the test until you passed it. You kept having to take it, and a lot of us took it for 6 straight months. That's not how your brain works. You know how your brain works? You use it, you look it up enough. I can guarantee you that after a few weeks of using this chart on a daily basis, doing chemistry problems, you will no longer have to look up nitrate. You're just going to know it. You know, you're not going to learn all the weird ones. What's something we don't use too? We don't use dichromate all that often. You might not remember that, but you'll know. Oh, dichromate. That's a polyatomic anion, and you will know where to go look it up. It would be stupid to have you memorize this. So, for some practice, and it looks like most of you who already did this are good, but for some practice and some hints and tips and tricks, let's look at this guy. When you look at this, remember the first thing to do in terms of naming is to break it apart. You know that sodium stands alone. You know that NO3 is a polyatomic ion. You name the compound simply for its pieces. So what is this called? Tell somebody sitting at your table. So this is sodium nitrate. Let me tell you the most common thing, the most common mistake people make, and they don't start making it until we start mixing all these together. What they do is they say sodium nitrogen oxide, because you want to name each part of it. Here's what I'm going to tell you. Nothing that we are dealing with is going to have more than 2 pieces. So when you see anything that is multiple pieces, that's a polyatomic. Nothing you're dealing with is going to have more than 2 pieces. So if I ask you for the formula for ammonium phosphate, first step. So first step is writing the ions. We have NH41+, and who's got the phosphate ion? Somebody at this island? P3 1-. Check your ion. Okay, we've got PO4 3-. So our next step, just like writing anything for an ionic, is a crisscross with one subtle distinction. Note that I put parentheses around both of those. You're not going to need it for both of them once you do the cleanup. 3 and 1. Since that's a 1, we don't need to state it. It's obvious. But what that parentheses around the ammonium does is set that apart. You cannot, when you are writing a formula, you cannot distribute that 3. Do not write N3H12. That would be wrong. And don't write something like that without the parentheses. That is also wrong. So that's a big, giant red flag, hint, star, highlight kind of thing. Let me give you an example of where people make that mistake. Calcium hydroxide. Easy for me to say. Calcium hydroxide. First step, give me an ion. Who's got a calcium ion for me? Go for it. Ca2+. Give me a hydroxide ion. Middle table. Who's got hydroxide? Okay, we've got our ions written. Now we do the crisscross. Got our ions written. We're going to do the crisscross. We get a 1 and a 2. So, correct final formula? CaOH parentheses. And very often, and I don't know where I picked this up. I don't know if I picked it up from a chem prof someplace. I will say that as CaOH 2 times, indicating that 2 times, indicating the difference between CaOH2. So let me show you what that looks like. This is the correct answer. Let me show you the wrong answer. So the wrong answer that people give is this. That is wrong. That's not the correct formula. And I'll show you why. This is 1 calcium ion and 2 hydroxide ions. Whoops. 2 plus. OH1 minus. OH1 minus. That's what that is. This, on the other hand, is a calcium and an oxygen and 2 hydrogens. There's not even a way to draw it because it's just wrong. That doesn't have 2 oxygen. That doesn't have 2 hydroxide ions. That has 1 oxygen atom and 2 hydrogens. So, okay.